Okay, Mr. G here, and this is a lesson that deals with friction. Oh, shoot, my stylus is not working. Hang on. Apple Pencil. Okay, let's try this again. Friction. So friction is a force that opposes slipping. Slipping. Friction does not oppose motion. It opposes slipping between two surfaces that are in contact with each other. Friction makes motion possible. Yeah, think about friction between your tires and the road. That's a good thing, especially when it's snowing outside like it is now. So friction is a force that opposes slipping, and I'm going to represent frictional forces using a lowercase f for friction. And so we've done some problems with friction already. So let's just do a couple of simple ones here that don't involve a whole lot of math. Let's see. So friction opposes slipping. So here we go. It's a level surface, and here's a big box on the surface. Okay, and here's the guy pushing this big box. Oof. Okay, and this guy is exerting a force against the box. And that's an applied force. I'll use a capital F. And let's say that that force is 500 newtons. All right. He is pushing against this thing with a force of 500 newtons. And it's not moving. Okay. So why isn't it moving? Well, because there's friction between the box and the floor, and that friction opposes slipping between the two surfaces. And the causes of that friction have to do with what's going on between these two surfaces. It can get complicated, but we're not going to worry about the complications here. Friction is like a sticky stick between the surface that wants to oppose slipping between surfaces. And so, yeah, if it's not moving, well, let's see here. Newton's second law says that net force is ma. And if it's not moving, that means the acceleration of this box is 0. And so m times 0 is a big fat 0. All right, so that means that the net force on it is 0. So there's got to be some force acting opposite of this force, and that force is friction. And the force is acting down here. I'm going to draw it on the box, so like this. All right, so there's friction. And so in this case, those two forces are equal to each other. Or if you wanted to get technical about it, we could say that the net force, which is this big F, minus the little f is 0, and that means that they're equal to each other. So that means that that frictional force is also 500 newtons, but it's to the left. All right. If he pushes harder, that frictional force can change. You think about it, because he can push it with a little force, he can push it with a little more force, and it takes a certain minimum force to get the thing moving, which means that this frictional force is actually changing. If he pushes it a little bit, that frictional force is little. If he pushes it harder, that frictional force becomes larger, up to a point, depending on what the surfaces are made of. At some point, it is going to start to accelerate, where that force that's applied is greater than the maximum frictional force. And so this also means there are two different kinds of friction. Oh no, if it's If the surfaces are not moving relative to each other, this is called static friction. And so static friction could be differentiated from slipping friction or kinetic friction by putting a little subscript here for static. We'll get more into the differences between slipping and non-slipping friction. So let's try another one like this, okay? Same guy, same box. It's a big pink box. Okay, right here. But this time he's really serious. Oh man, he's going to push that box till it starts to move. So now the box is sliding. With constant speed. Okay, the box is sliding with constant speed. And in order to achieve that, this guy has to exert a force here. Oh my goodness gracious. Larry is coughing over there. Larry, you okay, buddy? Bird, you all right? Okay, he's okay. So now he's pushing this thing with a force of 700 newtons. And the box is sliding with constant speed. So what's the story now with friction? Is there still friction? Is it greater than 700 newtons? Is it less than 700 newtons? What is going on here? Well, the key is to realize here what this is saying here. Constant speed. If the speed is constant, that means the speed is not changing. It means that the motion of the box, it's not speeding up, it's not slowing down, it's not making a turn, it's moving with constant speed. And this implies that the acceleration of the box, yeah, it's still zero, okay? If it's sitting still or if it's moving with constant velocity, the acceleration is zero in both cases. So if the acceleration is zero, net force is ma. Well, this means that net force is zero. And if the net force is zero, that means there's a frictional force acting on the box this way. And yes, it's equal to 700 newtons. All right. Since the box is now sliding, the nature of this frictional force is a little bit different. If it's slipping, this is now called kinetic friction. And that could be denoted with a little subscript here, F sub K. So there's kinetic friction if it's slipping, and there's static friction if there's no slipping. All right. Let's try another problem here. All right. Inclined plane. That's not a very good line. Let's try that again. Much better. So here, this is a ramp, an inclined plane. Let's say the angle here is 30 degrees. And there's a box sitting on here. And let's say that box has a mass of 2 kilograms. And the box is not moving. Okay, it's not slipping down this ramp. And so what keeps it from slipping? It's friction between the box and the ramp. Right, so we want to find out how large is that frictional force. And which way does it point? So we'll start this off by making a free body diagram of this box. So for sure, gravity is acting on the box. That's equal to mg. And it points straight down. And in this case, we can say it's 20 newtons. M is 2, and the value of little g is 10. Right, so 2 kilograms times 10 meters per second squared. 2 times 10 is 20, and a kilogram meter per second squared is a newton. So there's 20 newtons acting down on it. That's gravitational force between the box and the earth. Then there's a normal force acting perpendicular to the surface. N is this way. And the other thing about inclined planes and objects on inclined planes is what we do with gravity. Gravity, in this case, I know the gravity force is pointing straight down, but that force is wanting to move or exerting the force on the box in 2 different directions. In other words, you can look at gravity here as having components. Part of gravity wants to make this thing slip down the hill. All right, so there's a component of gravity acting parallel to the ramp, and we've talked about this. That component of gravity depends on the angle theta right here, and it is equal to mg sine theta. And there's a component of gravity acting perpendicular to the ramp, pushing the box into the ramp, and that component is mg cosine of theta. So for objects on an inclined plane, what we're doing here is rotating the coordinate system. Normally, a coordinate system we're using looks like this, xy. But it's easier to do problems like this if I use a rotated coordinate system like this. And so really the direction here of motion that we're interested in is along the ramp. And once you have these 2 components of mg, you really don't even need to worry about this guy right here. And so friction is parallel to the surface. And so to keep the box from slipping down the incline, friction is acting upward. And again, this is static friction because the box is not slipping. And again, if the box is not moving, well, once again, that means the acceleration is 0. That means that the net force on the box is 0. And that means that this frictional force is going to be equal to mg sine theta. All right, and so let's plug in the numbers now and figure out what that is. So mg, we already know that's 20 newtons. So 20 newtons times sine of 30 degrees. Sine of 30 is 1/2. So 20 times 0.5 is 10 newtons. All right. Larry, what are you doing? He's snooting around for crumbles of cookies because I was having a cookie earlier. Silly puppy. Okay. So that's good for a quick introduction to friction. I'll post some more of these in a little bit. All right.